Hello everyone. This presentation is about the rhodamine dye and its photophysical properties. Rhodamine is a family of dyes in which different types of dyes are present, such as rhodamine 6G, rhodamine 123, rhodamine B, etc. All these rhodamine dyes can be used as chemosensors. So chemosensor basically means a chemical compound or dye which can sense or detect the presence of metal ions in the sample. It is the core structure of rhodamine. It is called as the core structure because the structures of the rhodamine dyes are consist of this particular structure with a little bit variation in it. This structure consists of a xanthine compound in which a phenyl ring is attached, and there are also two amine groups are directly attached to it. To explain the presence of the above core structure in the structures of the rhodamine dyes, we can take an example, that is rhodamine 6G. So it is the structure of rhodamine 6G dye in which we can clearly see the presence of the above core structure, uh, and there are some little bit variations are also present in the side groups, which leads to the formation of the structure of rhodamine 6G. Rhodamine-based chemosensors are widely used for the detection of various metal ions in biological systems, industries, etc. Rhodamine derivatives remain colorless and non-fluorescent when their spirolectrum ring remains in closed form. However, this shows pink or purple color and strongly fluorescent nature upon opening of the spirolectrum ring. Opening of the spirolectrum ring takes place when the metal ion binds to it, and this binding process can be explained by the help of the host-guest relationship. So it is the host-guest relationship between the chemosensor and the metal ion. Uh, so here the chemosensor behave as the host and the sample act as the guest. So it is a rhodamine based chemosensor, and it is a sample in which the metal ion is present, and it is the binding site of this chemosensor. When the sample which consists of the metal ion comes closer to it, it binds with it like this, and due to the binding of the sample which contains the metal ion with the chemosensor, the opening of the spirolectrum ring takes place and the compound shows fluorescent nature or pink color. We know that there are various metal ions present in our body in the form of ferrin, catalase, vitamin B12, hemoglobin, carboxypeptidase A, etc. If the quantity of these essential metal ions decreases or increases in the body, then it can cause severe health issues. Hence, to detect the presence of metal ions and with required quantity, we can use these chemosensors of rhodamine family. Rhodamine dye can detect the presence of various metal ions such as Fe plus 3 ion, Hg plus 2 ion, Cu plus 2 ion, Au plus 3 ion, etc., which are explained below. So before discussing about the detection of the metal ions, let me tell you guys one thing, that there are various rhodamine based chemosensors are present for the detection of various metal ions. So now we can proceed to the detection of the metal ions. First, we will discuss the detection of the ferric ion. So to detect the presence of the ferric ion in a sample, we can use a rhodamine-based chemosensor, that is rhodamine polyethylene glycol. So it is the structure of rhodamine polyethylene glycol uh, when it when it reacts with the sample which consists of the ferric ion. The ferric ion binds with the binding site of the rhodamine based chemosensor like this, and due to the binding of the ferric ion, the opening of the spirolectrum ring takes place and the compound shows color. So next is the binding of Hg plus 2 ion. So to um, so for the detection of Hg plus 2 ion, a rhodamine based chemosensor is used, that is rhodamine diphenyl selenium. So it is the structure of rhodamine diphenyl selenium, uh, and it is the binding site of it where the Hg plus 2 ion gets attached like this, and due to this attachment, the opening of the spirolectrum ring takes place and the compound shows color. Next is the detection of Cu plus 2 ion. For the detection of Cu plus 2 ion, a rhodamine based chemosensor is used, that is dinitrophenyl rhodamine. So it is the structure of dinitrophenyl rhodamine, in which it is the binding site or spiral. It is the binding site of it where the Cu plus 2 ion gets attached like this, and due to the attachment of the Cu plus 2 ion, the opening of the spirolectrum ring takes place, and hence the compound shows color. So next is the detection of Au plus 3 ion. So for the detection of Au plus 3 ion, a rhodamine based chemosensor is used, that is agarose rhodamine lactone. So it is the structure of agarose rhodamine lactone in which it is the binding site of it where the Au plus 3 ion gets attached like this, and due to this attachment, the opening of the spirolectrum ring takes place, hence the compound shows color. It is an image of a spectroscopic machine which is known as UV visible spectrophotometer, and it is the image of another spectroscopic machine which is known as spectrofluorophotometer. It is a normalized absorption spectra of rhodamine 6G dye in different solvents taken by UV visible spectrophotometer, and these are the used solvents here. And it is the normalized fluorescence emission spectra of rhodamine 6G dye in different solvents taken by the above spectrofluorophotometer. And these are the solvents which we have used. These are the values we have taken from the above spectra. Here is the list of the solvents we have used. All these solvents are the polar solvents. These are the lambda max absorption values. These are the lambda max emission values. And these are the stock shift values. Stock shift is basically the difference between the lambda max absorption and lambda max emission. The above value shows that solvents have minimal role on the absorption and emission spectra of the dye. The lambda max absorption was observed between 526 to 532 nm, and the lambda max emission was observed between 549 to 554 nm respectively. The stock shift was observed between 21 to 23 nm. So from the above information, we concluded that rhodamine dye shows very good photophysical properties which can be used to solve various environmental as well as biological problems.